Hi, Algebra 2 friends. Here we are with section 10.5, base E and natural logarithms. So our vocabulary for today starts off with the natural base or the number E. And so just as we know pi to be a number that is irrational, amongst the ranks of irrational numbers is E. E is a number that is found in nature in a variety of ways, and it will be really interesting to look it up. The mathematician Leonard Euler, spelled like this, discovered, I guess is the way of saying it, the number E, and so it was given his, letter, initial, in respect. Okay, so with that in mind, that'll give you a little bit to look up. What is E? E is approximately 2.71828, and it continues on as we know irrational numbers do, like its friend pi. And so this number we will be working on, but you don't have to memorize it. Your calculator has an E button. And so you might realize that for the most part, your math teachers do not use E as a variable because we know that it is a number. All right, so the natural base exponential function is an exponential function where E is the base. So we're used to exponential functions of the form y equals a times b to the x power, but in this case, the b value would be replaced by e. So functions of the form y equals a times e to the x power would have a natural base. Natural logarithm, well, if you can write an exponential with e, you can also have a log base e. Log base e is called the natural log. So log base e of any number is called the natural log. Let's say log base e of 5, right? But the way we write that is ln because it is the natural log. The natural log is what we call it. The other one, you remember when it was just log with no number here, it's the common log. That was the last section. And this one is the natural log. And so we would write natural log or log base e of 5 as ln 5 or natural log of 5. And so that's where we're getting the natural logarithmic function, y equals the natural log of x, which can be graphed like this when we take into account the relationship between the natural log of x and the natural base exponent, e to the x. We know that they are inverses of one another, and therefore their graphs will reflect over the y equals x line. So with these next two problems, what we really want to do is just practice using our calculator, making sure that you can use your calculator to find this information. So whatever calculator you're using, please get it out. And I'm going to give you a couple of seconds. You can pause me, of course, to find the value. So find E, figure out how to raise it to the second power, find that value, find E to the negative 1.3 value. And that's what we're doing here. And then when we're dealing with the logarithm, the natural logarithm, I want you to find the natural log of 4 and see if you can, figure out the proper keystroke for your calculator. If you're using Desmos, it works a little bit differently. So go ahead and pause me. Okay, now your answers, I'm going to reveal them. The reveal. Voomp, voom, voom. How come it's not working? Oh, there it is. All right. That nervous feeling when you're like, what is happening? Okay, so this is what we have, right? We've got, hopefully, some people would need to use just different keystrokes. I'm not even going to explain what calculator they're using here. All right, so you should have gotten 7.389 and about 0.272 for the next one. And then for the natural log of 4, 1.386, and the natural log of 0.05, you've got negative 2.99. All right, let's look at example 3. Here in example 3 and 4, we're going to write an equivalent expression so we can solve these values. So an equivalent expression for this would be and you know how we do, it would be log. We're going to write this exponential as a log. Log base e of 5 is equal to x. Well, we don't write log base e of 5, we write the natural log of 5 is equal to x. And now that you've used your calculator and you can actually just plug it in and get the answer, do that now. So with my calculator, I'm getting 1.609. And I know we weren't asked to do that, but I think it's decent practice anyway. All right, let's try this next one. What we're asked to do is to rewrite this logarithmic as an exponential. Know that this is really just log base e of x is approximately equal to 0.6931. And therefore, this means that e to the power of 0.6931 is equal to x. And if you want to, plug it in and let's see what we get. So when I used my calculator, I got that x is equal to 2. All right, let's go ahead and take a look at these next two examples. We have e to the power of the natural log of 7. Now let's remember what this means again. We've got e to the power of log base e of 7. So remember, let's think a little bit about what this number is here. This number refers to the exponent that I would raise e to in order to get 7. This number here that's highlighted is the exponent that I would raise e to in order to get 7. Well, if that's this exponent, then this answer, when I raise e to that said exponent, it has to be 7. All right, I'm hoping that's making a little bit more sense. Let's take a look at this one. Over here, we've got natural log of e to the 4x plus 3 power. And so what that means is log base e of e to the 4x plus 3 power. And so here again, it's kind of like a canceling out. It's like an undoing. Hopefully you see that they're inverses and you get 4x plus 3y. Well, this is saying e raised to what power is e to the 4x plus 3? E raised to what power is e to the 4x plus 3? Well, it has to be raised to the 4x plus 3. So now we get to have fun using base e and solving equations. So what we're going to do is isolate this part of the problem. So I'm going to have my 5e to the negative x power minus 7. Well, let's move the minus 7 over to the other side. So if I do that, I'm going to add 7 to both sides, and it'll be equal to 9. Further isolating e to the negative x power, I'm going to divide both sides by 5, and I'm going to get 9/5. The next thing I'm going to do is take the natural log of both sides. When I take the natural log of e to the negative x power, I have to take the natural log of 9 over 5. But these guys cancel each other out, kind of like the problems we were working on before. So this side is really just negative x, which is pretty cool because that's what I want. I want x by itself. And over here, we still have the natural log of 9/5. We want to get rid of this negative so we can divide the negative on both sides, and we get that x is equal to negative the natural log of 9 over 5. And I know what you're going to do. I'm going to do the same thing too. I'm going to go and grab my calculator and plug this in, and when I do, you can pause me if you'd like, but when I do, I get something close to 0.5857, 0.5878, and it's negative. Here in example 6, we're going to be talking about one of the most common uses of E. It's when we consider calculating the amount of money someone will have in the bank at a particular time. And so I need to describe a little things to you. So A is the amount of money that person will have. P is the principal amount, the amount they originally put in the bank. The E is the number we all know and love but will not memorize, 2.718 something something. R refers to the rate, the percent interest rate that's given, and T is the time in years. All right, so with that in mind, let's see what we can do with this equation. Suppose you deposit $1,000 in an account paying 5% annual interest rate compounded continuously. Now, this phrase, compounded continuously, really tells us to use this formula. There are other formulas and they look like this. They're formulas where the money isn't compounded continuously. What's happening here, it's compounded periodically. In this formula, it's compounded on a yearly basis, and in this formula, it's compounded on an n number of times a year basis. I'd like to talk to you about this personally in a video. It doesn't work as easily as I'd like, but if you are passionate, certainly you can look up another video and find any teacher would happily explain this to you, but I like to do this in person, so we'll discuss. So these are periodic compounding of interest, whereas this is continuous. So as soon as you see compounded continuously, you should know that we are referring to an equation with E in it. All right, we're returning to the formula with E in it. All right, with that said, let's go ahead and break it down. So we want to know the amount of money. So we're looking for A after depositing $1,000 in the bank at a particular rate of 5%. And we will write the 5% as 0.05. Remember, R is the rate and T is the time. So this first part of the problem asks us to calculate this balance after 10 years. So you guessed it, we're just going to substitute 10 right in for T. Wanted to organize this a little bit, but we plug in 10 for T because that's the number of years. We're going to multiply those two, and then we can put it all in our calculator. So with the push of the button, we get that the value that this particular account will be worth would be $1,648.72. That's after 10 years of being compounded continuously at a rate of 5%. Let's look at part B. How long does it take for the balance in your account to reach $1,500? We know it's going to be less than 10 years, right? So this is how we'd handle that. We set up the $1,500 or $1,500 as the amount we're searching for. And then we're going to put in all the other information. We need to start off with the same amount, $1,000, e to the, remember we're putting it in at a rate of 5%, but the T is what we're looking at. So you know how to solve for this right now. We need to isolate this part of the problem. Let me highlight what I'm talking about. We need to isolate that by dividing both sides by 1,000. There, a little bit more room. When I do that, we end up with 3/2 is equal to e to this power. And so we want to get that exponent out of there. We want to bring the exponent down. And so we need to kind of cancel out the e. I know that sounds weird, but we're going to take the natural log of both sides. When I do that, the right side becomes simply 0.05t, and on the left side, I have the natural log of 3/2. This is where we're going to get our calculator involved. Well, not quite. We can also divide both sides by 0.05. I like to do all of the work, honestly, before we bring our calculator into the mix so we can just plug it all in. Now, we can use our calculator and take the natural log of 3/2 and divide it by 0.5. So we get that T is equal to 8.11. So a little bit over 8 years it will take for this to happen. And I'm looking at the problem again. It says, how long will it take for the balance in your account to reach at least $1,500? And so that means that T has to be at least, the smallest T can be, I should turn that the other way, the smallest T can be would be 8.11, meaning T could be greater, it could be more time. So we can write this as an inequality.